to the students. In online, some students is from in my group, in my Chinese students. Yeah. Professor Yue Zhongqi is from Hong Kong University. He is major in the geotechnical engineering. Hey, Professor Yue, please say hello to everyone.
Okay. Thank you for inviting me to do the pre-assessment. It's a pleasure. Thank you.
Yeah. The second professor is from Tongji University, Professor Yuan Yong. Professor Yuan.
Hello,
Professor Yong.
Yeah. Hello, everyone.
Yeah. The third professor is from our university, is Liu Zhaobao. Hello, Professor Liu.
Hello, everyone. Nice to be here.
Yeah. 李耀子很帅。Professor Xu Tao.
Hello, everyone.
Yeah.
Good evening. Hello.
Professor Jia Peng.
Hello, everyone.
Hello.
Professor Jia. 你打开摄像头没？打开那个摄像头。
Can you see me?
Yes,
I can see myself.
I can see you.
Okay.
Professor Jia, you are fine.
Hello, Professor Yue, Professor Yuan. Glad to meet you.
Hello. Okay. Mr. Israr and Mr. Zhuer. Today, Mr. Israr is the first to give the presentation. Maybe now invite Professor Yue, Professor Chair. This is the defense.
Okay. So today is pre-assessment, so you may make a presentation, and we give you comments. Then you might, but I'm not sure you will write down or someone will write down for you. Okay. So then we can let us know what you have done, and then we give you comments, and you modify this, right? Do I need to modify this, right? And then we get a final assessment. So that's good practice. Okay. So I have your thesis already, but today is pre-run. I mean, that's for quality control. Okay. So if everyone feels you are okay, then you might be able to go to the formal presentation or defense. Otherwise, you might have to do it again. Okay. So try your best, to convince us you have done a good job. Okay. Thank you. Right. So we will give comments after your presentation. The presentation should be limited time. So about 30 minutes, no more, right? Or 40 minutes. So then we give you comments. Okay. So I'm normally 30 or 40 minutes, okay? But it cannot more than 1 hour. Okay, maybe too much. Okay. So you might have only 20 minutes, will be trouble, right? Too short is not good. Okay, thank you. And you might try to run the first one. First one is Israr, right?
Oh, okay. Yes, sir. Thank you very much, sir, and welcome to all teachers, respected teachers. I am Muhammad Israr Khan, and I am sharing my screen to start my presentation. This is my PPT. I hope it is visible to all. It's okay?
Yes, you can go now.
Okay, so my PhD topic is slope stability analysis to predict the slope behavior in detail. And Professor Shuhong Wang is my supervisor. Well, this is my coursework. I have completed 16 credit hours, and this is just details regarding my coursework, which I have studied in my PhD. Well, the importance of my research topic is slope stability analysis is one of the most challenging field for researchers and designers. It is because the behavior of soil is different in different conditions and very uncertain due to the composition of soil. Different composition and material properties can change the analysis results. Similarly, seismic and non-seismic analysis will also give different results. So saturated and unsaturated conditions also affect the behavior of soil. Considering all the different conditions, this research is done to study and examine the slope stability of soil slopes in detail. Well, this research contains 10 chapters. Number first is slope stability analysis to develop correlations between different soil parameters and factor of safety using regression analysis. This is one topic. Chapter 2 is developing correlations for advanced prediction of slope factor of safety using linear regression analysis. And one case study is also considered in this one. Analysis of earth-fill hydraulic dam with varying crust length and permeability to develop correlations. Number 4 is comparing the various slope stability methods to find the optimum method for calculating factor of slope safety. Chapter 5 is seismic analysis of a soil slope to develop correlations for factor of safety considering horizontal and vertical seismic coefficients. Chapter 6 is comparative study of slope stability of a highway constructed in hilly area using limit, equilibrium, and finite element methods. Chapter 7 is comparative study of seismic and non-seismic analysis of a soil slope to develop correlations for factor of safety considering horizontal and vertical seismic coefficients. Similarly, Chapter 8 is a comparative study of soil slope using finite element and limit equilibrium methods to develop correlations for factor of safety. Chapter 9 is experimental analysis to find factor of safety in case of dams and slopes using finite element and limit equilibrium methods. And Chapter 10 is slope stability analysis to correlate shear strength with slope angle and shear stress by considering saturated and unsaturated seismic conditions. So all these chapters basically I have explained in 10 phases. Introduction is Chapter 1, Phase 1 is Chapter 2, Phase 2 is Chapter 3, Phase 3 is Chapter 4, and so on. Up to Phase 10. Well, this is a very long presentation, but I will try my level best to explain it in this very limited time. Landsliding is a big problem throughout the world, and many researchers are working and investigating to solve this issue and to minimize the landsliding issues in all over the world. These are some pictures. You can just see that, of course, landsliding is a big problem. It can damage the houses, it can damage the roads, and many problems it can create. So therefore, researchers always busy to minimize this problem. This is another picture. It is from Washington, USA, where you can see this landslide happens. This is another big, huge landslide. You can see this has totally blocked the highway. So therefore, this is just to show, in short, we can say that landsliding is a big problem faced by the world, due to which hundreds and thousands of people lost their lives, and it destroyed many important structures and hence damaging economy of our country. While the main objective of this research is to study the soil slopes in detail and to correlate all important parameters to each other, all this investigation could be used for better analysis of any soil slope, and hence it will minimize the landsliding issues. Well, Chapter 2 is Phase 1, and the title is Regression Analysis to Develop Correlation Equations between Slope Factor of Safety and Different Soil Parameters. In this phase, basically what I did, that the variation of soil properties from place to place, the factor of safety may differ too. Therefore, it needs to be studied and stabilized according to the specific site condition. Every site properties are different. So in this phase, I did these two points. Number one is insert nails inside the slope, with this technique is called nailing, and another technique I use that is called stepping. And this technique is, you can see this is basically nailing. I have analyzed this one, and this is called stepping. This is number 2. These 2 points I have worked on these, and I have developed some correlations. Correlations among the factor of safety values with the variation of cohesion, friction, and unit weight are developed. If the cohesion and unit weight are changing, so of course the factor of safety will change. So the results achieved in Phase 1 are: number 1, correlations between soil parameters in different conditions; number 2, variation in shear strengths in graphical form; and number 3, variation in factor of safety value in graphical form. Well, this is the material properties table. You can see the material number, total 20 number of materials were considered. This is cohesion, this is friction, and this is unit weight of all the material. So this table shows the material properties in this phase. This is the methodology. Number first is to find material properties such as cohesion, friction, and unit weight in the laboratory. Number two is model the slope using slide software. Slide is a software which I have used in this phase. Number 3 point is find the factor of safety for each material type. And number 4 is find correlation using SPSS and MS Excel. These two are softwares which are normally used for developing correlation. SPSS stands for Social Programming Software. Well, this is the model in which I have considered in phase 1. This is a slope, this is the soil model, and this table, this small table, shows the coordinates of this model. For example, this point is 0, 0, this point is 27, 0, and so on. So this table shows the coordinates, and this is the whole model. This is the step model. This is the step model, and this is the nail model when I did nailing. So all these 3 types I have analyzed, and I have each nail has an anchored capacity of 100 kilonewton, and it is an anchored nail type material. This graph basically shows the shear strength achieved in the natural form. I mean the natural slope. It is not stepped, it is not nailed. This is natural slope. So this is the shear strength achieved for all the 20 types of material. This graph is for the step slope when I did stepping. So you can see this zigzag graph which is changing. The shear strength also changes with the changing the model into stepped form. The shear strength also changes. Similarly, this is for the nailed form from material 1 to 20. This is the shear strength graph for the nailed model, and for all the 20 types of material. So phase 1, this is the factor of safety. FS stands for factor of safety. So this column shows the factor of safety in natural form. This shows in step form. This number 4 column is factor of safety when I inserted 3 meter nail, 3 meter. And number 5th is when I inserted 8 meter nail. So you can see this table clearly shows that the factor of safety changes when I did stepping, when I did nailing. So it gives different factor of safety. So maximum shear strength graphs are plotted for 3 meter and 8 meter only. It is clear from the previous table that in case of increasing the nail length, the factor of safety also increased. In case of material 1, the factor of safety is increased from 1.091. 1.091 is totally unsafe. I mean, if it is less than 1.5, it is unsafe. And when I did stepping and nailing, so the factor of safety, average factor of safety changes to 1.545, which is now safe. 1.5 and above is safe. So correlations between factor of safety and soil parameters. One of the main outcomes in this phase is the development of correlations between factor of safety with varying the values of cohesion, friction, and unit weight, which you can see in this table. This table shows, this is the main outcome of this phase 1. The correlations develop in natural and natural, stepped, and nailed form. So this table shows all the correlations which are developed in this phase. This is the main outcome of this analysis, where Fs is the slope factor of safety, gamma is unit weight, P is friction, C is cohesion, and R square is the percentage variation coefficient. So all these correlations are developed in this phase. You can see for different correlation in which step factor of safety is considered as dependent variable, while natural and nailed are considered as independent variables. So all these correlations are developed in this phase. And this graph shows the percentage improvement in factor of safety and shear strength. I mean, for every, you can see 3 meter nail, 4 meter, 5 meter, 6 meter, 7 meter, and 8 meter. All of them give different factor of safety. All of them gives different factor of safety. And natural stepping, again, this is the factor of safety in all 3 conditions, such as natural, stepping, and nailing form. So these 2 graphs are the main outcome in this phase 1. So the statistical results can be checked in these graphs. From the previous 2 figures, it is very clear that stepping can improve the factor of safety more than the natural and nailing form. it is clear that the shear strength can be improved from minimum to 13 kilonewton up to maximum of 77 kilonewton. I mean, this much we can improve the shear strength of a soil. If we apply these two different, for example, stepping and nailing, we can improve the shear strength of the slope. And similarly, while it can be improved from a minimum of 7 kilonewton up to a maximum of 82 kilonewton per square meter in case of material 20. It also depends on the material type. So this is a very lengthy conclusion, which I already explained. So I think no need to read this again. The previous slides already explained all this conclusion. So this is just, the summary of this phase 1. Chapter 3, phase 2 is linear regression analysis to develop correlations to predict slope factor of safety in advance. So again, this is just literature regarding this phase. I will skip this because the time is very short. So this slope model is considered in this phase. The coordinates are given, and in this phase, basically this slope angle is changing, and it is to observe that how much it affects the factor of safety. Again, this is the methodology flowchart, which is almost same like the phase 1. And 4 steps. This work is done in 4 steps. For example, saturated non-seismic analysis, unsaturated non-seismic analysis, saturated seismic analysis, and unsaturated seismic. These 4 conditions are applied, and in this phase 2. This is the material properties table again: cohesion, friction, unit weight, and material type. This is the slope model, and these 2 correlations are developed. The final average correlation between factor of safety, this is FS stand for factor of safety, and beta is the slope angle. In case of clay, came out to be this one, FS equal 1.836 minus 0.011 times slope angle. This is number 1, and this is the other equation. The final average correlation between factor of safety and beta in case of clay sand. The first one is in case of clay, and the other one is in case of clay sand. So these 2 correlations are developed in this phase. The final average, so this is basically the shear strength correlation in this phase between factor of safety and between shear strength and slope angle. Well, this is the condition number 2, which is called unsaturated non-seismic analysis. Again, correlations are developed after running and considering all the material properties. So this correlation is different because the condition is now changed. It is from saturated, it become unsaturated. You can see the water table applied on this slope model. This is unsaturated seismic analysis. Again, correlations developed in this phase, in this condition, and saturated seismic analysis. So these 2 correlations are developed in this phase. So these four conditions are considered, and these different correlations are developed using SPSS and slide software, which can be used in any project, in any design project, for landsliding and slope stability analysis projects. So case study also considered. There was a landslide in Karachi city of Pakistan, which I considered as a case study, and I used these equations to check that why this landslide happens. So it gives perfect result that the landslide was basically an unstable landslide, and the factor of safety was less than 1 at the time of failure. So the equations give perfect result when I match them. I have written the details in my thesis. So this is the conclusion, which is again a lengthy slide, which I will skip to read because it will take too much time, which I already explained in my previous slides. So this is basically the conclusion that these correlations are developed, all these different correlations developed, which can be seen in my thesis in detail. Well, chapter 4 is phase 3, developing correlations with varying permeability and crust length in case of a hydraulic dam. So this is some literature review regarding this work. So I would like to skip this one because this research phase is conducted in 2 steps. First the soil slope was modeled in the software, and secondly to develop correlation among slope factor of safety and seepage. And this work, the third thing which I considered is basically seepage of our dam. So this is the material properties table. This is the dam model. You can see this huge dam model. the coordinates are given, which is also called slope model. These are the properties, the seepage on the downstream slope and on the when the permeability of the dam was considered as 1 e raised to power minus 7, and when the permeability was changed, so the factor of safety also changed. I mean, on the downstream side, it also affected the seepage. You can see this analysis was run. This head was 80 meter. This is 0.028 cubic meter per day, and this was 0.013 per cubic meter per day. This dam was divided into different layers, into 7 parts almost, having different material properties. I have changed the material properties that, for example, how it will affect the seepage if I am using different material. For example, if the soil is rigid, if the soil is soft, if the soil is hard, so how it will affect the seepage. Because normally a dam designer used good material to compact and to make the dam model, so that the seepage should be at the seepage must be less. So the factor of slope safety in this stage comes out to be 4.934. The discharge on the downstream side was noted to be 4.9 into 10 power minus 15 cubic meter per day on slope face, while it was recorded to be 2.6 into 10 power minus 16 cubic meter per day on the bottom face. It shows that the discharge in case of the layers has less compared to the homogeneous slope, and it is a positive sign to have less discharge. So basically, this table shows the discharge values. When the crust length was 675 meter. In the first point, the crust length was 975 meter. In this second one, the crust length is now 675 meter. And this is for when the crust length is 375 meter. So this table shows the seepage value, the seepage quantity, that how much seepage it is occurring. And these are the correlation between factor of safety in empty and filled reservoir, when there was no water and when there was when the water was added. So the factor of safety, you can see this yellow, the orange one shows the empty reservoir factor of safety, and the gray color shows the factor of safety in when it was filled with water. So it is again different, I mean different factor of safety. This is for 675 meter crust and this is for 375 meter crust. And this is the final correlation when the factor of safety when there is no water in the dam will be equal to 0.03 times when the factor of safety equal to the 0.03 times when it is filled with water, when the dam reservoir is filled with water. So this correlation is developed in this space using all these different crust length 675, 375 and so on. So this is the summary. The total seepage will always be seepage on slope plus seepage on bottom face. This is the conclusion. Equation number 4.1 and 4.2 can be applied to find out the variation in seepage and slope factor of safety in any dam or embankment design projects. With various soil layers and properties in a soil slope, the seepage and slope factor of safety is also changed because it depends on soil permeability and layering. And number 3, the mean variation in seepage came out to be 3% with difference of permeability as 10%. So this I already explained in the previous slides. This is the conclusion of this phase. Now chapter 5 is phase 4 is computation of optimum slope factor of safety by comparing different slope stability methods. Well, there are various methods to design slopes and know about the factor of safety. There are various methods to analyze the slope stability which are summarized by Duncan. This is a scientist who work on these things. The methods normally followed in analyzing slope stability issues are Bishop simplified, Bishop modified, Yambu simplified and corrected, Spencer, Jelly, Morgan. All these methods are normally used. This is the summary of all these methods, their assumptions and their equations. The methods and their equilibrium condition, what they are considering, what they are not. This is basically the literature review of this phase. This is also the literature, which I will skip because the time is too short. This is the slope model which I have considered. This part shows the road. You can see normally in hilly mountainous areas, this is the mountain, and here we have a road, and again it is like this way. So we need to analyze the safety of this slope. All these are the material number, the material properties, cohesion, and this is the angle of repose. Angle of repose means slope angle, unit weight friction, and all these methods are run and analyzed in this space. You can see this in this method. So to check that why and how much is the difference in the results of all these methods. I mean, Bishop is giving different result, ordinary Fellini is giving another result. The difference is very less, very minute, but still there is some difference. So in this phase, I have checked the difference, that how much is the difference in this phase. So this graph basically shows the variation. This is the factor of safety, and these are different methods: Bishop, simplified, Fellinius, Yambu, corrected, Spence, all these methods. So you can see for the same model, the factor of safety is different. For example, Bishop simplified give 1.702. Ordinary Fellinius for the same slope gives 1.631. Yambu simplified gives 1.616. I mean, they are not same. They are different, a little minute difference, but still they are different. So normally in such a case, we always consider the optimum one. I mean the lesser one. And in this one, this is material 2. This is material 3. And in case of material number 1, the maximum value of slope factor of safety is 1.705, given by corps of engineer analysis method, while the minimum value of slope factor of safety is 1.616, given by Yambu simplified analysis method. The overall mean value of slope factor of safety by all the analysis methods comes out to be 1.684. That is very near to the value given by Spencer analysis. Basically, the summary, the conclusion was that Spencer normally gives good results. I mean, Spencer gives the optimum result because all the methods were considered, and the overall view of this analysis was that Spencer analysis results are the most perfect. Similarly, in case of material 2, the maximum value for slope factor of safety is 1.669, given by corps of engineer number 2 analysis method, and the minimum value of the slope factor of safety is 1.59, given by Yambu simplified analysis method. The overall mean value of slope factor of safety by all the analysis methods comes out to be 1.642. That is very near to the value given by Yambu corrected analysis. And in case of material 3, it was again Spencer. It was again Spencer. So chapter 6 is developing correlations for slope factor of safety in case of horizontal and vertical seismic considerations. So here again, seismic consideration, the seismic analysis, which is also called dynamic analysis, is performed. So this is literature. I would like to skip this. In this phase, a total of 24 number of analyses are performed, 24 number. On a predefined soil slope, the slope angle, which is also called angle of repose, varied from 30 to 45 degrees. And the horizontal seismic coefficient was considered as 0.04 minimum and 0.15 maximum, according to the recommendations. In this paper, the recommendations are given. And the vertical seismic coefficients are considered in a range of 0.0124 minimum and 0.04 maximum. So these are basically from the previous literature, which can be seen in reference number 93. And the slide software is used for the analysis. The difference of slope factor of safety is mentioned in graphical form in the results section for all the cases. This is the same slope model was considered. The coordinates are also given 70, 30, 58, 30, and so on. This table gives the overall overview of this analysis. This is the analysis summary. You can see the factor of safety table is given for this is the horizontal seismic horizontal coefficient, and this is vertical seismic coefficient. So when it was 0.04, this was the factor of safety. When it was 0.10, this was the factor. So with the change of the horizontal coefficient, seismic coefficient, the factor of safety is changing, which is given in this table. Considering horizontal seismic coefficient, HSC stands for horizontal seismic coefficient, and keeping vertical seismic coefficient as 0, this correlation is developed. And the applicability is 99.7%. I mean, it is almost 100%. It is applicable. Considering vertical seismic coefficient and keeping horizontal seismic coefficient as 0, this equation 6.2 is developed, and the applicability is 99.89%. This basically F stands for factor of safety equal minus 0.4243 times vertical seismic coefficient plus 1.4739. And similarly, considering both horizontal and vertical seismic coefficients, this correlation is developed, equation 6.3, and the applicability is 99.67%. And number 4 is the applicability is 99.67%. So this is the conclusion. Equation number 6.1 and number 6.2 can be used to compute the slope factor of safety if only horizontal seismic coefficients and vertical seismic coefficients respectively are considered. Equation number 6.3 and number 6.4 can be used for computing the slope factor of safety if both horizontal seismic coefficients and vertical seismic coefficients are considered. In any further future research work, all these analysis results can also be compared to normal slope stability analysis, where seismic coefficients are to be kept zero, so that to get a clear understanding of the variation between seismic and non-seismic analysis. So this was chapter 6. Do I have more time? Because still I have 3 chapters remaining.
Okay, you can go.
Okay, thank you. So I will quickly finish, I hope, because only 3 chapters remaining, and I'm trying my level best to complete them. Chapter 7 is phase 6, comparison of slope factor of safety results achieved by limit equilibrium and finite element methods in case of a highway constructed adjacent to a hill. So this is the literature regarding this phase 6. Phase 6 of this research work is examining the difference of results achieved by using finite element, FE stands for finite element method, 2D analysis, with limit equilibrium method, 2D analysis for a homogeneous soil slope, which is a predefined slope in a hill having rod. Well, this is the rod, this is the slope model, here is the rod, this is angle of repose, and all the coordinates are given. And in this one, I used a finite element method, finite element, not limit equilibrium. So this table shows the slope factor of safety by using finite element method. This is the summary of this analysis: material, cohesion, angle of repose, unit weight, friction, road width. I mean, this column shows the road width, different road width, not same. I mean 6 meter, 15 meter, 22 meter, 28 meter. So many I have considered in this one. And this is the factor of safety. This column, the second last column, shows the factor of safety in case of finite element. This one, finite element. And this one shows the factor of safety in limited equilibrium case. So again, they are not same. Finite element method give 1.463 and limit equilibrium give 1.644. I mean, they are not same. So normally we take the lesser one, 1.463, because we are not going to take much risk. So the summary is that finite element gives more good results, more optimum results. It took more time, and it is I would say very difficult, but still the results are good using finite element method. Not limit equilibrium are simple and they took very less time, but the results are not that much good as compared to finite element methods. So these are the graphs, the factor of safety graphs for material 1, material 2. And this blue shows finite element factor of safety, and yellow, orange shows limit equilibrium. So you can see the variation, the difference for the same material, for the same slope model, but the factor of safety is different using finite element and using limit equilibrium. This for material 3, this for material 4, this for material 5, this for material 6, and the material details can be seen in the table. So in short, from these graphs, a correlation between limit equilibrium and finite element methods came out to be finite element factor of safety equals 0.88 times limit equilibrium. This is the summary of this phase 6. So equation number 7.1 can be used as a cross check to find out the value of slope factor of safety in both limit equilibrium and finite element methods. It will provide a comparison of both methods and factor of safety achieved for same slope using these two methods. This equation is valid only for homogeneous slope only. Moreover, this equation does not include the influence of pore water pressure and seismic loads. In future work, maybe I will consider pore water pressure and seismic loads as well. And there is still open space for research on this topic to investigate both finite element and limit equilibrium methods, considering the rainfall effects. I mean, rainfall is another problem. seismic loads and effect of underground tunneling on slopes. Chapter 8 is seismic slope stability analysis of a predefined soil slope to develop correlations between seismic and non-seismic factor of safety. Well, this is literature, and I will only read this one. By keeping the previous research in consideration, this part is done in 4 phases. Non-seismic analysis to find out the slope factor of safety, analysis by considering the horizontal seismic coefficient while ignoring vertical effect, analysis by considering the vertical seismic coefficient while ignoring horizontal effect, analysis by considering both the horizontal and vertical seismic coefficients. And 36 number of slope analysis were performed on a predefined soil slope. The slope angle was in range of 30 to 45 degrees. The horizontal seismic coefficient was considered as 0.05 to 0.15 as recommended in this paper, in this literature, while the vertical seismic coefficient were in range of 0.015 to 0.05. Slide software is used for limit equilibrium analysis in this phase 7. So again, this is the slope model. Cohesion range is 11 kilonewton to 13 kilonewton per square meter. Angle of repose is 30 to 45 with 5 degrees interval. Unit weight is 14 kilonewton per cubic meter. Angle of internal friction is 31 to 33 degrees. Horizontal seismic coefficient is this much, and vertical seismic coefficient is this much. This table shows the summary in which you can see the case number, cohesion, angle of repose, unit weight, friction angle, horizontal coefficient, vertical coefficient, non-seismic factor of safety, and seismic factor of safety. These 2 columns, I mean this one, this column, and this column. These 2 columns are the factor of safety values when the seismic coefficient is considered and the seismic coefficients are not considered. I mean, normally engineers analyze slopes by not considering the seismic effects, which is not good. They must consider the seismic effect, because you can see in this table clearly that non-seismic give 1.631 and seismic give 1.451. I mean, this is less. They will design it for 1.631, but it will, in fact, it will be 1.451, which is lesser than 1.631. So this is the recommendation that they must perform seismic analysis, not non-seismic. Non-seismic is not good. And figure number 73 to 76 mentions the slope factor of safety graphs in case when only horizontal seismic coefficient is considered, while the vertical seismic coefficient is 0. And figure number 77 to 80 mentions the slope factor of safety graphs in case when only vertical seismic coefficient are considered, while the horizontal seismic coefficient are 0. Again, figure number 81 to 84 mentions the slope factor of safety graph in case when both the seismic coefficient, horizontal and vertical, are considered. All these are the graphs. SFS stand for seismic factor of safety, and NSFS stand for non-seismic factor of safety. So these correlations are developed and the graphs are given for case 1, case 2, case 3, case 4, case 5, case 6, case 7, case 8, which is the case number and details are given in the previous table. Case 9 up to case 10 and 11 and 12. So finally, considering horizontal and keeping vertical seismic coefficient as 0, this yellow equation 8.1 is developed, which you can see seismic factor of safety equal minus 2.4145 times non-seismic factor of safety plus 4.9285. This is equation number 1 from figure 89, 90, 91 and 92. And similarly from figure 93 to 96, equation 8.2 is developed. From figure 97 to 100, equation 8.3 is developed. And you can see the applicability for equation 8.1 is 95%, 95.4. For equation 8.2 is 99.81%. And for equation 8.3 is 95.84%. And this is the conclusion which I already explained. So I think there is no need to explain again. Chapter 9, phase 8, comparative study of slope factor of safety achieved by limit equilibrium and finite element methods using nailing and stepping technique. So this is the literature regarding this phase. In this phase, you can see the stable material properties, cohesion, friction, unit weight, Phase 2 is a very useful two-dimensional finite software which is used for soil and rock slopes stability analysis. Phase 2 can be used for many engineering projects which include excavation design, slope stability analysis, groundwater seepage analysis, probabilistic analysis, consolidation and dynamic analysis, etc. Three-dimensional finite element slope stability analysis program is described in detail by Smith and Griffith. So this is the literature regarding this phase. There are 20 different types of material used in case of limit equilibrium method which are mentioned in table 335. For simplification purpose, in this paper, 5 out of 20 materials are taken for plotting the comparison graphs between limit and finite element methods. Those 5 selected materials are material 1, material 5, material 10, and material 15 and material 20. So this table shows the details. Factor of safety values in case of finite element method for material 1, material 5, material 10, 15, and 20. So this table clearly shows the variation in the values of factor of safety, such as in natural form, it is less compared to step form. Step form gives less factor of safety compared to nail form. Moreover, with the increase of nail length, the factor of safety is increased, which can be seen in table 38. And this is table 39 for material 1 to material 20. Factor of safety values in case of limit equilibrium method. The first one was finite element, and this second one is limit equilibrium method. So this graph results comparison for material 1. Figure 87 to 91 shows the difference of results between limit equilibrium method and finite element method for different slope conditions and by variation of nail length, which are mentioned in each figure. This is for material 1, the factor of safety, finite element, and limit equilibrium methods. This is for material 5. This is for material 10, material 15, material 20. And finally, a mean value for all these 5 cases will give the final correlation equation as below. Equation 9.3. Limit equilibrium factor of safety equal 1.89 times factor of safety given by finite element method, minus 0.86. And the applicability of this equation is 82%. And similarly, equation applicability, hence we can write this equation in case of factor of safety as factor of safety in case of limit equilibrium equals 1.89 times factor of safety in case of finite element minus 0.86, which is the final correlation in this phase. So this is the conclusion which I already explained. So I will skip this slide. And chapter 10, phase 9, analysis to compute the slope factor of safety for a predefined dam using limit equilibrium and finite element methods. So all the below charts and methods are considered in this phase, and correlations are provided at the end. Taylor and Peck charts, Bishop and Morgenstern chart, Morgenstern, Spencer, Hunter and Schuster, experimental and computer programs. In this phase, 20 different types of soil materials are used to analyze and calculate the correlation for factor of safety in 3 different conditions, such as natural, stepped, and nailed form. A software namely slide is used for the analysis. This experimental analysis is very useful to know about the factor of safety in case of dams and slopes adjacent to any highway constructed in hills and mountainous regions. This is the material table, which shows all the properties. And the final correlation equation, CE stands for correlation equation for computing the slope factor of safety in case of finite element methods are mentioned in table, this one, table 41. With the cohesion variation, these are the correlations. With friction variation, these are the correlations. And with unit weight variation, these are the correlations. And the applicability value you can see 99%, 100%, 100%, 99%, 99%, 99%, 98%, 98%, and 99%. So the applicability is very good, almost 100%. So correlations provided in table 41 can be used to compute the slope factor of safety without running the finite element procedures. I mean, the finite element procedures are very lengthy, so we can use the correlations to get the results. The applicability of all these equations is in range of 98 to 100%. I mean, very high. And normally limit equilibrium methods and finite element analysis methods give very symmetric results in case of non-complex geometries, but the results are much different in case of complex slopes. These equations can be used to cross-check the difference of results in natural, stepped, and nailed slopes. And my final chapter 11, phase 10 is slope stability analysis to correlate shear strength with slope angle and shear stress by considering saturated and unsaturated seismic conditions. So this literature I will skip. This is the slope model considered in this phase. You can see horizontal seismic coefficient equal 0.3, slope angle, coordinates, everything given. This is the methodology flow chart. So these are the factor of safety in case of saturated seismic analysis. Factor of safety value in case of material 1. It is clear from figure 11 that increasing slope angle, factor of safety will decrease with a constant rate. The factor of safety values are, for material 1 in case of the saturated seismic condition are 0.624, 0.608 and up to 0.510. Similarly, analysis was conducted for all material types and its summary is provided in table 43 and 44 along with factor of safety values. So this table provides the summary of this analysis. Tau stands for shear strength and sigma stands for shear stress. So this table basically provides the summary of this phase 10. Excuse me, I just want to plug this mouse. Well, this table 45 shows the correlation in case of clay saturated seismic case. You can see the material number and the shear strength and the correlation, which is 34.572 minus 0.434 times slope angle plus this one, and the applicability, you can see the applicability values 99.4%. So these are the correlations in case of clay. And another is unsaturated seismic analysis. So these are the factor of safety in this case, unsaturated. Considering the material properties mentioned in table 1, all the input values are analyzed in slide, and finally table 46 and 47 are achieved, which shows the shear strength and shear stress values for material 1 to 5 and 6 to 10. These two tables are achieved in this second phase. These are the correlations developed in case of unsaturated seismic case. The first one was saturated and the second one is unsaturated. So this is the conclusion that soil slope in two different conditions such as saturated and unsaturated conditions are analyzed, which with considering the horizontal seismic coefficients, 200 types of material properties were considered, and finally correlations between shear strength, slope angle and shear stress are developed as equation 11.2 and 11.3. From equation 11.2 and 11.3, it is clear that more the value of slope angle and shear stress, less will be the value of shear strength. The variation could be checked for any slope stability case. For any other slope stability project, the shear strength could be simply obtained by applying equation 11.2 and 11.3. So this is the summary, which I already explained. Well, these are some abbreviations which I used in my thesis. FS stands for factor of safety, LE stands for limit equilibrium, FE stands for finite element, SS stands for shear strength, CE stands for correlation equations, SSS stands for slope stability analysis, C stands for cohesion, SPSS is a software statistical package for social sciences, RS stands for regression analysis, gamma stands for unit weight, and phi stands for friction angle. These are some papers which I published from my research from all these 11 chapters. 8 are already published, 8 papers, and these 2 are already almost accepted, and hopefully they will get online very soon. So almost 10 papers I have published from this work. This is acknowledgement. Okay. So these are all references. Almost.
So you finished? Okay.
Yes.
So you used about